The fuselage is the main structure or body of the aircraft and carries the passengers and crew in safe, comfortable conditions. It also provides space for controls, accessories and other equipment. It transfers loads to and from the main planes or wings, the tailplane, fin, landing gear and, in certain configurations, the power plants. There are three main types of construction in use. First, there is the truss or framework type, which is generally used for light, non-pressurized aircraft. Then there is monocoque. And finally, semi-monocoque, which is in use on most other aircraft. The last two types of structure are more generally referred to as stressed skin. The framework consists of light-gauge steel tubes welded together to form a space frame of triangular shape to give the most rigid of geometric forms. Each tube carries a specific load, the magnitude of which depends on whether the aircraft is airborne or on the ground. It's a strong, easily constructed and relatively trouble-free basic structure. The framework is covered by a lightweight aluminium alloy or fabric skin to give an enclosed, aerodynamically efficient load-carrying compartment. Monocoque is a French word meaning single shell. In a monocoque structure, all the loads are taken by a stressed skin with just light internal frames or formers to give the required shape. Sandwich construction, which is a honeycomb core with a skin of aluminium alloy or composite material, such as glass-reinforced plastic or carbon fibre-reinforced plastic, can be used to provide rigidity and strength. Even slight damage to the skin can seriously weaken the structure. To be a true monocoque, the structure would have no apertures in it at all, but for practical purposes they have to be provided for access and maintenance. The apertures have to be reinforced so that the integrity of the structure is maintained. Once the aircraft doors are closed and all the hatches and access panels are fitted, the fuselage is, to all intents and purposes, a monocoque structure. As aircraft became larger and the air loads greater, the pure monocoque structure was found not to be strong enough. Additional structural members known as longerons were added to run lengthwise along the fuselage, joining the frames together. The light alloy skin is then attached to the frames and longerons by riveting or adhesive bonding. Longerons stiffen the skin and assist the sheet materials to carry loads along their length. This gives us the semi-monocoque type of construction. This is the most common type of construction used in modern light aircraft. When cutouts are made to stressed skin structures, for example to provide access panels, doors or windows, or when repairs are required to damaged areas, reinforcement in the form of doublers or backing plates is required around the cutout. Bulkheads are set in place to separate the different sections of the aircraft, for instance the engine compartment from the passenger compartment. The bulkhead has the same basic shape as the frame or former, but almost completely isolates one compartment from the other. Having said that, some holes will have to be made in a bulkhead in order to allow control fittings, pipework, and electrical cables to pass through. Bulkheads are usually much more substantially built than the frames, because they are subject to greater loads. The bulkhead, which separates the engine from the passenger compartment, serves to prevent the passage of fire from the engine rearwards, and will do so for some time, although not indefinitely. The wings support the weight of the aircraft in the air, and so must have sufficient strength and stiffness to be able to do this. Their strength and stiffness are determined by the thickness of the wing, with the thickness and type of construction used being dependent on the speed requirements of the aircraft. The types of construction are biplane, braced monoplane, and cantilever monoplane. Very few biplanes fly at more than 200 knots in level flight, so the air loads are low, which means that a truss-type design which is covered in fabric is satisfactory. The wing spars, interplane struts and bracing wires form a lattice girder of great rigidity, which is highly resistant to bending and twisting. Unfortunately, it also generates a relatively large amount of drag, which accounts for the fact that biplanes fly relatively slowly. This type of design is also used on low-speed aircraft, although it's very popular with manufacturers such as Cessna, whose aircraft can hardly be said to be slow. One of the most famous braced monoplanes was the Spirit of St. Louis that Charles Lindbergh piloted in his epic solo transatlantic flight. Let's now look at cantilever wings. The main planes have to absorb the stresses due to lift and drag in flight and, if of cantilever design, their own weight when on the ground. This is achieved by building the wing around one or more main load-bearing members known as spars, which are constructed so that they will absorb downwards bending stresses when on the ground and the upwards, rearwards and twisting stresses when in flight. The major structural components of the wings are generally manufactured from aluminium alloys, with composite materials such as glass-reinforced plastic, carbon-reinforced plastic and honeycomb structures being used for fairings, control surfaces and flaps, etc. Bending stress relief is also provided by positioning the major fuel tanks within the wing. Main planes may be of single-spar, twin-spar or multi-spar construction. A conventional structure would consist of front and rear spars, the metal skin attached to the spar to form a torsion box. The skin takes the loads due to differences in air pressure and the mass and inertia of the fuel in the wing tanks. It generates direct stresses in a spanwise direction as a response to bending moments and also reacts against twisting. Stringers are spanwise members which give the wing rigidity by stiffening the skin in compression. Formers, or ribs as they are sometimes called, maintain the aerofoil shape of the wings, support the spars, stringers and skin against buckling, and pass concentrated loads from engines, landing gear and control surfaces into the skin and spars. The tail unit, or stabilizing unit, sometimes called the empennage, comes in many different designs. It can be conventional, T-tail, H-tail, or V-tail. Some aircraft have their longitudinal stability and control provided by foreplanes, canards. The horizontal surfaces, which are known as the tailplane or horizontal stabilizer, provide longitudinal stability by generating upwards or downwards forces as required. The vertical surfaces, the vertical stabilizer or fin, generate sideways forces as required. Longitudinal control is provided by either the elevators or the moving tailplane, depending on design. Directional control is provided by the rudder. Both the tailplane and the fin are subject to both bending and torsional stresses. Structurally, the tail unit components are generally smaller versions of the main planes, in that they use spars, ribs, stringers and skin in their construction. On some aircraft they may also be sealed to provide fuel storage space. They also use the same basic materials. For instance, aluminium alloys or composites with honeycomb structures. High-density expanding foam is sometimes used within control surfaces to provide greater stiffness at lower weight. For steady flight, the aircraft must be in a state of balance, 0 moments around the axes, and the flying controls enable this to be achieved for all possible configurations and centre of gravity positions. Secondly, the controls will be required to manoeuvre the aircraft around its 3 axes. The principle of operation of all of the flying controls is explained in the subject Principles of Flight. Here in this lesson we only consider them as part of the aircraft structure. Rotation around the longitudinal axis is rolling and is controlled by the ailerons. Rotation around the lateral axis is pitching and is controlled by the elevators or by a moving tailplane. Rotation around the normal axis is yawing and is controlled by the rudder. On some aircraft, rotation around two of the axes may be achieved with one control surface. For instance, the elevon, which is a mixture of elevator and aileron, is used on tailless aircraft to give both pitching and rolling. The ruddervator, which is the name of the control surfaces on a V-tail aircraft, enables both pitching and yawing. The stabilator is a movable tailplane combining the dual function of horizontal stabilizer and elevator. That is, it gives both longitudinal stability and control. The movement of the flying control surfaces in response to the movement of the cockpit controls in light aircraft is achieved mechanically. This means that the control surfaces are connected directly to the cockpit controls by a system of cables, rods, levers and chains. Each control can be obtained through the use of either elevators, flying tailplanes or canard control. For the purpose of this lesson, we'll assume that our aircraft has elevators fitted to the tailplane. If that is the case, then rearward movement of the control column causes upward movement of the elevator, which causes the aircraft to pitch nose upwards, and vice versa. Control in roll is achieved by ailerons. Turning the control wheel to the right causes the right aileron to move up and the left aileron to move down, giving roll to the right. Control in yaw is enabled by the rudder. Moving the right rudder pedal forward causes the rudder to move to the right and causes the aircraft to yaw to the right. The amount of movement of each control surface to either side of its neutral position is laid down so that the required control can be achieved over the full range of operating conditions. The movement is not necessarily the same each side of neutral. For example, an elevator usually has a greater deflection upwards than downwards. The limit of movement of the control surface is determined by a mechanical stop. The function of mechanical stops is to prevent excessive control surface deflection, which may cause the aircraft structure to be overstressed during normal operations. A stop which limits the movement of the control surface is called a primary stop. A stop which limits the movement of the control column or rudder pedals is called a secondary stop. When the primary stop is closed, there will be a small clearance at the secondary stop. Flutter is the rapid and uncontrolled oscillation of a flight control, or the surface to which it is attached, which occurs as a result of an unbalanced surface. Flutter is caused by the interaction of aerodynamic forces, inertia forces, and the elastic properties of the surface or structure, and can lead to the catastrophic failure of the structure. Flutter can be prevented by mass-balancing control surfaces to move the control surface centre of gravity closer to the hinge, and therefore alter the period of vibration. Flutter must not occur within the normal flight operating envelope of the aircraft. The fact that an aircraft is poorly maintained, particularly in respect to excessive control surface backlash or flexibility, may mean that flutter will occur at speeds below the limit airspeed. An aircraft is trimmed when it will maintain its attitude and speed without the pilot having to apply any force to the cockpit controls. If it's necessary for a control surface to be deflected to maintain balance of the aircraft, the pilot will need to apply a force to the cockpit control to hold the surface in its deflected position. This force may be reduced to zero by operation of the trim controls. The aircraft may need to be trimmed in pitch as a result of changes of speed, changes of power, or varying centre of gravity positions. Trimming in yaw will be needed as a result of changes in propeller torque, or if there is asymmetric power on a twin-engined aircraft. Trimming in roll is less likely to be needed, but would be required if there was a lateral displacement of the centre of gravity. For example, if the contents of the fuel tanks in each wing were allowed to become wildly different, or, in the case of a twin-engined aircraft, if one engine had failed. Aircraft are fitted with high-lift devices to reduce the take-off and landing distances. This permits operation at greater weights from given runway lengths and enables greater payloads to be carried. A flap is a hinged portion of the trailing edge which can be deflected downwards and so produce an increase of camber. There are various types of flap design which all increase both lift and drag in varying amounts. The most popular type of flap used on light aircraft is the plane or camber flap. This type of flap increases the camber of the wing when extended, and in doing so can increase the maximum lift of the wing by about 50%. Lowering flap will increase both the lift and the drag of the aircraft, but not in the same proportion. Selecting flap will cause a pitch change. The overall change of pitch will be influenced by the type of flap, the position of the wing, and the position of the tailplane. A tension, or tensile load, is one which tends to stretch a structural member. Components designed to resist tensile loads are known as ties. Compressive loads are the opposite of tensile loads and tend to shorten structural members. Components designed to resist compressive loads are known as struts. Shear is a force which tends to slide one face of the material over an adjacent face. Riveted joints are designed to resist shear forces. Bending of the structure involves the three basic loadings. They are tension as the outer edge stretches, compression as the inner edge squeezes together, and shear across the structure as the forces try to split it. Torsion or twisting forces produce tension at the outer edge, compression at the inner edge, and shear across the structure. Stress is the internal force inside a structural member which resists an externally applied force, and therefore a tensile load or force will set up a tensile stress, compression loads, and compressive stresses, etc. Stress is defined as the force per unit area and is measured in units of newtons per square millimetre. When an external force of sufficient magnitude acts on a structure, the structural dimensions change. This change is known as strain, and is the ratio of the change in length to the original length, and is a measure of the deformation of any loaded structure. Buckling occurs to thin sheet materials when they are subjected to end loads, and to ties if subjected to compressive forces. The maximum load that the designer would expect an airframe or component to experience in service is termed the design limit load. The design ultimate load is the design limit load times the safety factor. The minimum safety factor specified in design requirements is 1.5. The structure must withstand design ultimate load without collapse. The safety factor is the ratio of the design ultimate load to the design limit load. When an aircraft is parked in the open, strong or gusty winds could blow the controls about against their stops with sufficient force to cause mechanical damage. To prevent this occurring, control locks are fitted. These may be external, as shown here in the left and centre pictures. If the control locks are controlled from the cockpit, they may be arranged so that it is impossible to open the throttle until they are removed. Remember, control locks must be removed before flight.